Welcome to qnawire.
Okay, we've got several carboxylic acids, and we've got to arrange them in the order of increasing acidity. So here are the carboxylic acids. They're all 4-carbon chains. I'm drawing out the bond line drawings of them instead of the condensed formula as they did. It's just easier to look at, in my opinion. And I guess I'll just state outright that they are already in order of increasing acidity. That is, this is the most acidic, and this is the least acidic, and so forth. Okay. Why is that? It's worth discussing. Remember that acidity depends on the stability of the conjugate base, right? So let's consider the last structure we were given. The conjugate base is simply the same molecule, but instead of an OH, we have an oxygen with no proton. The proton has been lost, and it has a negative charge. And basically, the reason that there's a difference in these carboxylic acids is that there's fluorine and then the positioning of that fluorine. Now, recall that fluorine is strongly electronegative, right? So it draws electron density towards itself. And in that way, this negative charge, which resides here, and remember it's actually in resonance here, this negative charge is actually delocalized over this whole molecule and to some extent over this fluorine. And the closer that this fluorine is to the carboxylic acid functional group, the greater the added stability is of having this electron withdrawing group, right? So electron withdrawing groups stabilize acids, rather the conjugate bases of acids, and the closer the electron withdrawing group is to the acidic functional group, the stronger that stabilization is. Which is why the one that doesn't have the electron withdrawing group is the least, the next is the one that does, but it's the furthest away, the next is the next closest, and the next is the closest. Okay, next we've got pentane, 1-pentene, 2-pentanol, and 1-pentyne. And the question is, of these, which is the most acidic? Well, recall that oxygen-hydrogen bonds are way less strong than carbon-hydrogen bonds. The reason being that once that hydrogen leaves, remember, we're going to have O- conjugate base, and that's far more stable than C-, right? Carbon does not really like being an anion or a cation, whereas oxygen can handle being a cation or anion to some extent, right? It's rather electronegative. So if you've got the choice between a proton coming off of an oxygen or any of these carbons, you should pretty much always go with the oxygen. There's not many cases where a carbon is going to be more acidic than an oxygen, right? So I'm just going to label this 1 for most acidic. Okay, now we can ignore the oxygen and look at the difference between these three. They all have carbons, so no matter what, we're talking about a proton. And the difference here then would be the hybridization of the carbon with the proton, right? We've got sp3 hybridized carbon, we've got sp2 hybridized carbon, and we've got sp hybridized carbon, right? And that's the difference. So the question is, which of these carbons is going to be most stable as the conjugate base? That is, a primary carbanion an sp3 carbanion, an sp2 carbanion, or an sp carbanion, right? And I'll just tell you that it's going to be the sp. That's the second most acidic. Third most acidic is the sp2, and fourth most acidic is the sp3. Another reason for that is that recall that sp orbitals are comprised of an s and a p, and that then you form a hybrid orbital from this. You get something that looks like that. Well, in general, s orbitals have more density closer to the nucleus, right? If I draw the nucleus in blue here, there's the nucleus, right? It's pretty clear to see that s orbitals have a greater amount of density closer to the nucleus than do p orbitals, which have these kind of gaps, right? Because of the planar nodes, right? And for that reason, an sp orbital, which is hybridized from one s orbital and one p orbital, is closer to the nucleus on average than a hybrid orbital of a 1s and 2p orbitals, right? So this is sp, sp2. sp2 looks a little more like a p and spends more time further away from the nucleus, right? And that's even more pronounced when we get into sp3 orbitals, which, as you might imagine, are made of an s orbital and 3 p orbitals hybridizing, right? So remember, in each case, the nucleus is like right there, the nucleus is right there, the nucleus is right there, and the sp orbital has more density closer than the sp or the sp2, or than the sp2 or the sp3. And it's a negative charge, right? We're talking about dealing with a lone pair, and that lone pair would rather hang out closer to the nucleus than